I'm Hossein from Università della Svizzera Italiano, and in this presentation, I'm gonna to talk about our work in collaboration with University of Amsterdam and Leiden University on joint geographical and temporal modeling based on Metis factorization for point of interest recommendation. This is the outline of my presentation. Let me give you some introduction and the motivation of our work. Nowadays, with the development and popularity of mobile devices, a variety of location-based social networks helping the world, such as Foursquare, Facebook, Yelp, and so on. By introducing the check-in by Foursquare in 2009, people can share their information and interact with many location or POI or point of interest. The information can be time, geographical coordinates, social relationship or social situation, physical environment like weather, and a category that we call them contextual information. Also, location-based social networks are very popular. It is still very challenging for users to choose a location to visit, especially in to choose a location to visit, especially in a region, in new region or a new area. To overcome this challenge, it is very needed to build a POI recommendation or POI recommender system that is recommend the right location or POI to right user. The main contribution of our work is to address the data sparsity problem by jointly model of geographical and temporal information. Our purpose method that we call it STACP or Spatio-Temporal Activity Center Point of Interest Recommendation contains three different modules, SMF, TMF, and STAC. As a big picture of STACP, it takes a user POI check-in frequency matrix as an input, and each module generates a score for each user on each POI. And finally, we aggregate the scores as a final score that shows the interest of a user on a location. Let's see the details of each module. The first module is SMF or static matrix factorization. Like a traditional MF, it takes the whole of user POI matrix and construct users and items latent features based on that. The second module is a TMF or temporal matrix factorization. Both of SMF and TMF are based on check-in frequency matrix to consider users' preference on POIs, but TMF also into account the check-in time. So in TMF, we first split check-in frequency matrix based on different temporal state like weekday, weekend, working time, leisure time, or the day of the week, or something like that. And at the end, we aggregate the final scores of different temporal states to show the interest of a user on a POI based on the different temporal state of matrix factorization method. The third module is to consider contextual information to model user behavior. Here you see a sample user's spatiotemporal activity. As we see, users' behavior follows a geographical center-based model, and these centers are different based on different temporal state. So in first picture, we have all of user check-in. When we split this check-in based on the different temporal state, here we consider leisure time and working time, we can see the differentiate of the centers of the sample user. And to model the spatiotemporal activity center, we propose STAC score. This formula has two terms. In the first term, we calculate the S-score of POI belonging to the center of a user that is based on the distance. And in second term, we consider the effect of check-in frequency on the center. So now the challenge is to find the user's centers. So actually here we, in our case, in our paper, we model it as a linear interpolation under two temporal states based on the lambda parameter, and we consider working time and leisure time. To find the user centers, we propose an algorithm that we call it activity center allocation. This algorithm actually has three different blocks that we show by blue line here. In the first block, we actually rank all of the check-in location of a user based on the frequency of visit, and then after that we consider the first location of a user as a center, and we compute the distance between this location and the other location in the list, and if a distance is smaller than a parameter d, we add the new location to the center list. So finally, by this approach, we create a region based on these locations and the parameter d. Finally, to add this location as a center and this region as a new region to on a user center, we compute the ratio of the check-in frequency of centers on total frequency of user check-in, and if this ratio is greater than parameter alpha, then we add this region as a new region, and we consider its center as a center for a user. As to evaluation, the purpose approach, we use two well-known data sets, Goala and Foursquare. You can see the statistic of the data set on the table. We consider the earliest 70% check-in of a user as a terrain set, and 20% of tests, and 10% for validation. Here we can see the graph of and the graph of the parameter on the parameter d, alpha, and lambda based on two different metrics, recall at 20 and precision at 20. As you can see, we analyze this parameter on both data sets, Goala and Foursquare. You can read the more details about this analysis in our paper. To evaluation, we consider two variations of our model. The first variation, we called it STACP no CTX or no context. That here we, as you can see in picture, we remove the proposed contextual model, and we just consider the SMF score and TMF score. And the second one is STACP no TCP or no temporal center. Here we consider the the we calculate the user centers just based on spatial or geographical information, and we didn't consider the temporal information to compute the user's center, and we didn't differentiate between the user centers based on the different temporal states. The table shows the results of experiment based on the Guala dataset. As ECIR method obtains the best performance compared to the other POI recommendation methods. In terms of all of evaluation metrics, here we used precision at 10 at 20 and recall at 10 and 20 and NDCG. Results show that STACP beats all of geographical based methods in terms of all metrics. This is expected as the previous models only consider the basic idea of the geographical influence that users tend to visit nearby POIs, and also this shows the effectiveness of our users preference and the users contextual model, which consider both geographical and temporal information, a jointly model of users activity. And also we compare the performance of STACP with its variations. The goal here is to demonstrate the effect of the spatiotemporal activity centers on the performance of STACP, or our proposed method. We see that STACP improves STACP no TC by 42% in terms of recall at 20. Also, we see a statistically significant improvement of STACP over STACP no context in terms of all of evaluation metrics. The results of Foursquare is similar to what happened on Guala dataset. You can find more details on the paper about the analysis of the result on Foursquare datasets. In this experiment, our goal was to study the effect of data size on performance, as we call it, the sparsity problem. So we train our model and all baseline methods with different data sizes. To do so, for each user, we only consider a certain percentage of visited POIs in training datasets randomly, and we consider 40%, 60%, and 80% of training datasets. The results show that our model is more effective in comparison with the baselines as the training size varies. This shows that STACP is more robust when we don't have access to enough data from users. Thus, the purpose context models enables STACP to deal with noise and data sparsity more effectively. Also, you can see the results on Foursquare and dataset, and the result is similar to the Goala datasets, and our method is also more robust on rather than the other baseline on Foursquare datasets. Finally, in this paper, we propose a checking-based and context-based model for POI recommendation that we call it STACP, or Spatio-Temporal Activity Center Point of Interest Recommendation. Our model effectively model the user mobility patterns, and our contextual model is actually flexible to be incorporated by the other models. It means you can consider just our contextual model or STAC and incorporate it by the other POI recommendation models. And the dataset and code are open source, available at this URL. You can access them and on the GitHub. And I would like acknowledge the IR group of Università della Svizzera Italiano and Professor Fabio Kerestani for his support on this work. And also I would like this work actually supported by a Swiss state secretariat for education, research and innovation, mobility grant between Switzerland and Iran. And final thanks for your attention, and thank you so much.